An isentropic process is a process where the entropy remains constant, that is, S1 equals S2, or delta S is going to be 0. For my ideal gas, let's remember that delta S, one of the ways of evaluating this is CV logarithm of T2 over T1 plus R times the logarithm of V2 over V1. And this has to be equal to 0 in an isentropic process. So we can work this to get an expression, such that in this case we are going to have CV natural logarithm of T2 over T1. It's going to be, we're going to pass this term to the other side. Since there is going to be a negative there, we're going to get rid of that negative by inverting the ratio of volumes. We get rid of the natural logarithm, for instance. First, we can put this as a power, and then we get rid of the natural logarithm. Since natural logarithm of something has to be equal to the same thing, we can get rid of the natural logarithm, or we just plug an either, and then we have, for instance, this expression. This expression, we can work it out, so that we can have, for instance, T2 over T1 is going to be equal to V1 over V2 R over CV. Since R is going to be equal as well to CP minus CV, then we can get, for instance, that T2 over T1 is going to be equal to V1 over V2. CP over CV is K, the ratio of the specific heats, minus 1, and then we can work this out at the end by stating that this is going to be equal to T2 V2 to the K minus 1. K minus 1 only affecting the volume is equal to T1 V1 K minus 1. So this is one useful expression for isentropic process. Other useful expressions can be solved by equating the ideal gas equation to the original one that we have worked out, and we get these three expressions that relate, for instance, the pressure, temperature, and volume in terms of the ratio of specific heats being more or less 1.4 for the atomic molecules, such as, for instance, oxygen or air,